Thank you very much. Well, first, let me thank the organizers for their invitation. It's truly a pleasure to be here and to deliver these lectures. So, and let me also apologize in advance because there might be part of what I'm going to say which would be a bit redundant with what Rupert already presented essentially yesterday, but well, hopefully it will be nice for you to have two slightly different point of views on the same type of techniques, and well, I couldn't change everything in any case, so that's the way it is. So I will be talking about some asymptotic methods for oceanographic models. And so today's lecture will be devoted to some, let's say, to the presentation of the hierarchy of models. So what I will be doing today will be formal, essentially. Okay, there will be no rigorous proof or anything. The goal is just to present to you, to introduce the different models that I will be using and to get you used to them. And then in the other two lectures, I will present some mathematical tools to study these models, and I won't be doing the whole proofs of convergence, but I will be focusing on some specific issues that that are quite frequent in these types of models. So in the models that I will present, so you have already seen this in Rupert's talk, there are a lot of small parameters, there are some penalizations, and so some singular penalizations, and the idea is that these singular penalizations have a whole, let's say, tool set that come with them, a mathematical tool set. And so generically what they create is very strong waves propagating at very high speeds. And so you have so lecture number 2 will be dedicated to the treatment of such high frequency waves through filtering techniques. And another classical effect of these singular penalization is that they create boundary layers close to the boundary. So I will be dedicating lecture number 3 to boundary layer method. Okay. So for today, I will focus on the hierarchy of models, and I will start with the NavierStokes Fourier model because, like Rupert said, for us mathematicians, it's maybe the when we want to modelize a fluid, this is the first thing that we can think of, okay? So if you want to describe the ocean, then the first step is to identify all the variables that are going to describe the state of the fluid, okay? So the variables are the following. So it's the density rho, the velocity u, which is 3-dimensional, at least for now, the temperature, you also have the salinity and the pressure, which I will denote capital P to avoid any confusion with rho. Okay, and all these variables are linked together through a set of equations. But before writing down the set of equations, let me talk about the external forces on the fluid. So you have the interaction of the ocean with the atmosphere or with the wind, okay? And let me say right away that I will never be considering very sophisticated models regarding this interaction. Okay, so essentially, the most complicated thing that I will be doing is assume some kind of Neumann type condition for the velocity at the surface to modelize the wind. You have the rotation of the Earth. Which creates a Coriolis force. Okay. You have the interaction with the sun and the moon, which creates tides. Okay, but I will be neglecting those. Okay, I won't be talking about tides at all. It's not on the time and length scales that I will be considering. And there is an interaction with the boundary. Okay, so if you take all of this into account, yes, thank you. Okay. And gravity. Okay. And if you take all of this into account, the system that you obtain is the following. So you have conservation of mass, which is just a transport equation. You have conservation of momentum. So now I'll write the Coriolis force. Okay, so K is a unit vector orientated from the south pole to the north pole, okay, the rotation axis of the Earth. And omega is the angular velocity of the Earth. So it's 2 pi divided by 1 day. Okay. The pressure gradient. Then there's some, okay, then there is in the right-hand side the gravity. Okay, and E3 here is really the ER vector, okay, the one that is oriented the local vertical, okay. And then there are dissipation forces that I don't want to talk about right now. So this is dissipation. Okay, why don't I want to talk about dissipation? Because the thing is that in oceanographic models, the modeling of dissipation is an issue in itself, because actually what is observed is that the energy loss of, let's say, waves is much stronger than what you would expect if you only took into account, let's say, the molecular dissipation or something like that. So there is some additional dissipation phenomenon that is going on, and usually this is modelized through some kind of turbulent dissipation, okay? And one of the features of this turbulent dissipation tensor is that it is anisotropic, okay? So this is something that is important to keep in mind. The dissipation tensor is always anisotropic. Before and after I have put the equation in the non-dimension, in dimensionless form, okay? So keep in mind that there is some dissipation, that it's essentially a phenomenological modelization here, and I will write, as time goes on, some dissipation tensors, okay? So conservation of momentum, then there is conservation of energy. So I will write it in the following way. Rho Cp dt theta plus rho u gradient Cp. Gradient of theta plus P divergence of u equals kappa Laplacian of theta plus 2 tau du. So here I was hoping to keep everything on this board, but okay, yeah, I will use this one as well. So here tau is the viscous tensor. Okay, and du is the symmetric part of the gradient of u. Okay, and Cp is the thermal diffusivity of water. Thermal capacity, excuse me, thermal capacity. Okay, and there is the transport diffusion equation for the salinity. Which is just, so it's really a transport diffusion equation, okay? Is everything okay? No. No? Why? Who said no? Qu'est-ce qu'il y a? It's P, sorry, it's P div u.
And after, okay, and after
This one?
It's kappa, okay.
It's kappa, and Steven, I will put kappa T to say that it's the one for the temperature. Yeah. It's kappa Laplacian of theta. It's P div u. Yes, sorry. And yes.
Another question.
Yes.
You said dissipation in the momentum balance. You didn't want to go into details.
And then I wrote something for the conservation of energy. Let's say there is some quadratic term here that is consistent with what I'm putting here.
So D is just divergence of tau, isn't it?
Yes. Yes, in that case, it's just divergence of tau. And then the last thing is that you need to have some equation of state. Okay, so for the equation of state, actually, the equation of state for the ocean is not so first, not so easy to find, but you can find one in Gill, for instance. Okay, and once again, it's pretty phenomenological. So what he writes is something like that. So it's rho of S, theta, and P equals rho of S, theta, and 0 over 1 minus P over some function which I shouldn't be calling kappa A, let's say F of S, theta, and P. And he gives explicit expressions, let's say asymptotic expansions if you want, for this function and this one. Okay? But it's definitely not P equals rho to the power gamma. Okay? It's something that is much more complicated than that. And then you need to take some boundary conditions. So about boundary conditions, so it depends on which boundary you're looking at. So at let's say that you're going to modelize the domain. Yeah. if you were to be completely, I don't know, rigorous or close to the physical setting, then the fluid domain should be a domain depending on time, exactly with a free surface, exactly like what David said in his talk. The thing is, it's very complicated to treat the free surface, and actually, to my knowledge, there are relatively few works that do it with this full set of equations. Okay, especially when you take into account the viscous parts and everything. So you take a very strong stance, which is to say that you assume to have a rigid lead approximation. So the surface of the ocean is flat, there are no waves, and the surface of the ocean is just z equals 0. Okay? Surface is z equals 0. So the domain is just omega, which is, let's say, no, not omega, domain d. I don't think I have any d yet, which is some omega h for the horizontal part, times something like, okay. So it's, let's say, the x1, x2, x3 in R3 with x1, x2 in some domain omega h, and z between 0 and some function b of xh. Okay, so this is the most general domain that you can treat. And another thing to keep in mind is that usually it's not smooth at all. The bottom of the ocean really has a very rough shape with very strong amplitudes. Okay, so the average depth of the ocean is 4 kilometers, but this is also the order of magnitude of the mountains in the ocean. Okay, so the amplitude of the variations of the bottom are really of order 1 after you non-dimensionalize the equations. So on the surface, typically what you're going to assume is the following thing so you are going to assume that your horizontal velocity is equal to some tensor, not tau, sigma. So this is a tensor describing the interaction with the wind. Okay. You will also assume that your vertical velocity vanishes, so you have the non-penetration condition. Okay, and for the other, so you have no boundary condition for rho, and for theta and s, I never saw any strict consensus on what you could take. So, for instance, for the temperature, you could either argue that you have some kind of thermostat on the surface, and so you have a Dirichlet boundary condition, or that you impose some flux, because you have heating by the sun, and so you have a flux of energy going in. Okay, but in my point of view, both are legitimate boundary conditions. So for theta, you take either Neumann or Dirichlet. And for S, for the salinity, it's more reasonable to assume that you have no flux of the salinity at the surface. Okay, and on all other boundaries, so on the solid boundaries, you're going to assume that u equals 0. Okay, you have a friction on every solid boundary. Okay. And the most reasonable thing to do is also to assume Neumann boundary condition, so no flux for theta and s. Okay? So once you wrote all this, you supposedly have a closed set of equations. Okay? And the questions that you ask yourselves are the following. So the first question, maybe as a mathematician, is are the equations well posed? Okay? And in fact, if you take the pressure law that I wrote here with some dissipation tensor that is anisotropic, well, the well-posedness is not clear at all. Okay, it doesn't fall into any classical framework for compressible fluids, and it's really so. I'm pretty confident that it's true. It's something that we are working on, but it's not written anywhere. And it's something, if you want to make it work, you have to follow really the latest developments in that area. Okay? So the well-posedness is not clear for, at least for physically realistic pressure laws or viscous tensors. But if you are ready to, let's say, twist the models a bit and take equations of state that are close to, let's say, isentropic gases or something like that, then obviously you can use all the methodology that has been developed for compressible fluids, and then you will be able to prove some well-posedness. Okay? The other question is the qualitative and quantitative analysis. Okay, because, and I will come to this in a moment, so there are, as soon as you put the equations in a dimensionless form, you have a lot of small parameters within the system. Okay, and you can play around with them to derive some asymptotic limits. Okay, and so you can play around with them in the number of ways. This is something that Rupert described yesterday, and I will be coming back to it later on. And you can derive a lot of simplified models to allow you to, well, let's say, have a better, at least qualitative description of what's going on. And this is of interest in, in several levels, but in particular in numerical analysis, because if you want to have a numerical model that allows you to have a good description of your system, and if your system has very high oscillations, then you need to be very careful, obviously. Okay? And this theoretical analysis might help you either develop a scheme that will remove, let's say, some strong instabilities, or to modelize, instead of the original model, some simplified one that doesn't have all these strong waves. Okay? So I will talk a little bit about these two questions later on, but let me first talk about the dimensionless equations. So you can introduce a number of dimensionless parameters. So you choose the following typical scales or quantities. So first you have a horizontal scale. That I will denote L. And so here we're working on very large scale motions. So L will go typically from 100 to 10 to the 4 kilometers. And I will take, let's say, the middle value, which is 10,003 kilometers in when I will be doing some to computing the small parameters in what follows. On the other hand, you have a vertical scale, which is much smaller, which is typically 5 kilometers. Okay, so the ocean is really a thin layer, and this is something that I will be going back to in the following. You also pick typical horizontal velocity. And in what follows, I took a velocity which was like 5 centimeters per second. Okay. Typical temperature. Let's say capital theta, which would be 10 degrees Celsius. Okay, and the typical salinity is 35. So I don't exactly know actually what the unit of the salinity is. I don't know if it's just the concentration of salt or if it's already some kind of element non-dimensionalized thing, but this is the typical value you see everywhere, especially in the equation of state given by Guillaume. So I think it's definitely proportional to the concentration of salt. Okay, I don't know if it's exactly 35. I don't know, gram per liters or whatever. That seems a lot. But and with this, you can derive a number of small parameters. The first one is the Rossby number. So the Rossby number will measure the intensity of the rotation. Okay, so it's defined as the ratio between the typical velocity, horizontal velocity, and the horizontal velocity associated with rotation. Okay, and with the numbers I gave above, this is 10 to the minus 3 or 10 to the minus 4. Okay. Then you have the Froude number, which measures the intensity of the stratification, or of the, let's say, of the gravitation forces, and it's U over the square root of G times H. Okay, and again, it's like 10 to the minus 4.
Velocity by the shallow water waves.
So it's close to them. Okay.
Stratification.
Yeah, you would have to.
It's much slower than square root of GH.
Okay.
This would be the relevant Froude number if you had not a rigid lid, if you had an open.
Ah. Okay, but this is what we usually take. So what do you suggest we?
Well, you would have to scale the square root of GH with the stratification
yes.
effects of salinity and what have you. So
but then this is what you do. You do some kind of asymptotic expansion in terms of a small parameter for the density. And you also have one for the equation of state, actually. And maybe this is actually where the Froude number would enter. But within this equation of state, you have a small parameter hidden there. Then there's the aspect ratio. Delta, which is h over L, and which is 10 to the minus 3, essentially. Okay, and well, there's also the Mach number, but since I didn't define the local speed of sound, well, I'll write it anyway. So it's U over U star where u star is the local speed of sound. Okay, and once you have dimensionalized these equations, what you obtain is the following. So here you have 2 over the Rossby number. Here the pressure gradient becomes, I'm going to put it like that. You have the gradient of the pressure, and here you have the thin layer effect. Okay.
Number squared?
Yes, thank you. Then you have 1 over delta square times the Froude number to the square here. Okay, and yes, there's also the typical density that I forgot. Okay, which will be rho. So it's 1 kilogram per liter, so 10 to the power 3 kilogram. Okay. So that's it for the dimensionalization of these equations. And then you also undimensionalize the rest. Okay. So here the Laplacian becomes an isotropic okay, and I'm going to put, I'm just going to write some q tilde of u here, okay, to keep in mind that there is a nonlinear term associated with the dissipation here. So for the salinity, it's the same. Yes, so it's some kappa tilde. There is some coefficient. Same thing here. I'm dropping the tildes everywhere, but there are some tildes in the coefficient as well. Okay? So the important thing here is that you have small parameters here, here, and here. Okay? These are the most important ones. And these ones so are associated with singular penalizations. And it's typically this type of equation that we're going to study in the rest of the lectures. And they are going to create some higher frequency wave, such as the ones that Rupert described this morning. And they, yes, so they are going to create a number of singular behavior, okay? And so, so Rupert talked about this yesterday. Since you have several, at least 4 small parameters, you can do, and there are additional ones hidden in the equation of state that I didn't write in a non-dimensionalized form because it gets really messy, okay? But you can do a lot of things, okay? For instance, you can say, okay, well, in this equation, when I look at, let's say, the Rossby number compared to the square of the Froude number, the Rossby number is much lower than the square of the Froude number because both of them are of the same order. So you can choose to let the Froude number go to 0 and keep the Rossby number fixed. Or you can also say that both are equal and of the same size. But then what do you do about the aspect ratio? And so on. So there is one strategy that Rupert talked about yesterday, which is to take a distinguished limit and to say, okay, I'm going to link all these parameters together and to take one singular limit. And I have to say that I wish I had done this a number of times because he wrote a couple of papers not doing that, and it was really a mess. And I'm not sure that in the end it's very enlightening from the application point of view. So I strongly encourage you to do that and to take distinguished limits. Okay. So I 100% agree with what Rupert said yesterday. This being said, let me just add a few comments. So first, in the mathematical literature, this is not always what is done. There are a number of papers in which people do not take distinguished limits and consider these small parameters independently, and they let one go to 0, and then the other possibly go to 0, possibly in another paper. Okay? And so maybe to introduce the hierarchy of models today, this is what I'm going to do as well. Okay? Maybe because in some way it simplifies the presentation, because it allows me to present one limit after the other and to introduce you the different intermediate models in a, let's say, a sequential way. Okay? The other reason I would say, but from a more maybe pure mathematical point of view, is that sometimes in when you look at the whole range of parameters, you might encounter some special structure in some regimes that do not necessarily correspond to the actual physical regime that you would be considering. And sometimes it's quite tempting to actually look at that regime because it's very rich and it has a lot of structure and you want to study it, okay? And I think that it's actually a legitimate reason, okay? That you might want to look at a certain regime of parameters just because you have a very nice interaction between the different terms in that scaling, and, you know, why not, okay? So this is a justification in itself. It's just that you need to mention it and not use some kind of false argument, okay? The last reason that maybe to argue that in some cases it's nice to keep several small parameters is that in some cases you can actually do an analysis with a dependency of, well, let's say if you have two parameters, you can do an analysis by keeping the two parameters and describing the interplay between the two and the different regimes. So I will do that maybe in the last lecture about boundary layer methods. There is at least one model in which we were able to describe a whole range of regimes. And I think this was helpful to the physicists we were working with Laure Saint-Raymond and Roberta Bianchini, because it's somehow, they had some kind of intuition of what was the regime they wanted to work with, but this was not really justified from a modelization point of view. It was just, you know, I don't know how. They had some intuition that this was the correct regime, and we were able to justify it somehow. So, okay, in some cases it's nice to keep everybody. Okay, but so what I wanted to say is that in any case, what you're going to do is you are going to make a choice. Okay, about which parameters are going to 0, in which order, if there is an order, or how you're going to link them. And in fact, there was already a choice in everything that I wrote here. When I said that when you pick a horizontal scale or a typical horizontal velocity, you're already making a choice about the type of phenomenon that you're going to modelize. Okay? And the important thing is that in the end, so first, you need your assumptions in the beginning to be more or less accurate, okay? But the important thing is that the asymptotic model that you end up with actually describes the phenomenon that you wanted to describe in the first place, okay? This is what you ask of modelization. So I would say you can do everything as long as it's physically accurate and that it describes the model you wanted to describe in the first place. Okay, so this was my small message. Okay, so time is going on. Okay, so about the theoretical, the difficulty of difficulties associated with the analysis. So I'm going to go quite quickly about that because I wanted to present at least one asymptotic limit in this talk. So it's really the link to the singular penalization. Okay. And so I will be talking about filtering techniques tomorrow to give you a flavor of what can be done to remove this singular penalization. But let me just do one simple example on a toy model, which is an ODE. If you look at so the toy model, it will be the following one. So you consider the ODE u epsilon dot plus say I over u epsilon of t plus u epsilon of t square equals 0. Okay, so this is quite similar to what we have here because you have a singular penalization, and I wrote it with it's anti-symmetric, okay, which is consistent with what we have here. The spectrum of the Coriolis operator is imaginary. So in this toy model, so if you just look at it, then you see that even if u epsilon remains bounded, the derivative of u epsilon is not bounded because it has very high oscillations. And so, for instance, if you want to apply the Cauchy-Lipschitz theorem without looking at the structure of your system, you will have a very short existence time. And to prove that your existence time is larger than that, then you have to actually look into the structure of the penalization. And one way to get rid of the oscillations is to set v epsilon of t equals u epsilon of t exponential, and so I should it over epsilon, I guess, okay? So if u epsilon is bounded, v epsilon is bounded as well, okay? And then v epsilon, the derivative of v epsilon of t will just be v epsilon square times exponential plus or minus it over epsilon, minus it over epsilon. Okay. And then, so obviously, for this very simple ODE, you can integrate it, have an explicit formula and everything. Okay, but obviously in PDEs you cannot do that. So let me just give you an argument that I will repeat tomorrow for filtering techniques. So you start, let's say, from v epsilon equals 1. And you see that as long as v epsilon remains bounded, its derivative is bounded as well. Okay, so you inherit some compactness with respect to that. Okay, you can apply a Cauchy-Lipschitz theorem on an interval of size 1, and so you have compactness for v epsilon, and you inherit as well some compactness for your u epsilon, or at least weak compactness. So you know that your v epsilon will converge towards some v bar, and you can even prove. So if you have strong convergence of this one converges weakly to 0. You know that your v bar will have a 0 derivative in the end. Okay, if you have a strong convergence of this one, so you know that u epsilon will behave like some constant times exponential minus it over epsilon. Okay, just by doing, so this is called filtering the oscillation. And then you look at the filtered equation, you derive some compactness properties of the filtered equation, and it allows you to pass in the limit. So again, this is what I will be doing tomorrow for an hour and a half, so I won't go too much into the details. And so for the last part of today's talk, I wanted to talk about the hierarchy of models. Okay, so there is a there is one first limit that you can do, which is to go from the NavierStokes Fourier model to the Oberbeck-Boussinesq model. With a rotation. Okay. Actually, I wanted to do this one afterwards because I told Rupert that I would be talking about the derivation of the quasi-geostrophic model. So I would be. So let me just write down what the Oberbeck-Boussinesq model looks like, and then I will go from Oberbeck-Boussinesq to the quasi-geostrophic model. And if I have time, but I doubt it, I will talk about this limit today, but in any case, it will be a large part of tomorrow's lecture. So the Oberbeck-Boussinesq model looks like this. It's so if I don't write any small parameter, at least, it's an incompressible model. Yes, I need to add the rotation. Okay, you have divergence-free velocity, and for the temperature or the, let's say, the density, you have a viscous equation with an additional term. Okay, and this term here accounts actually for the variations in the stratification. This is the, okay, if I'm writing this n square, this is the Brunnweisela frequency, okay, which we're talking about today. So tomorrow, when I talk about the filtering techniques, the main example that I will be treating is precisely this limit, how you go from NavierStokes Fourier to Oberbeck-Boussinesq, okay? But for today, so what should I raise? For today, what I wanted to talk about was rather the limit from Oberbeck-Boussinesq with rotation to the quasi-geostrophic system. Okay, let me give you some references about that. So I think there was an article by Lyons, Stemam and Wang. Originally, there was works by Bill and Bourgeois. And then a lot of works by Chemin, Gallagher, Charles, and their students and co-authors. Okay, so I'm sorry if I missed anyone there. And so and Iftimi as well. So the starting point is this model, but with some penalization for the rotation and for the stratification. Okay, so you start with dt u eta plus u eta grad u eta. Okay, plus 1 over eta times the rotation term, plus the gradient of p eta, minus Laplacian u eta. And this is rho eta, obviously, okay? dt rho minus 1 over f eta u3 plus, and I will keep, and everything is divergence free. Okay? And you investigate this limit as eta goes to 0. Okay, maybe just before I do that, a couple of things that I didn't mention. When I wrote here the Coriolis force, I told you that this was the north-south vector, okay? And you can see that here I replaced it with the local vertical vector. Okay, this approximation is quite classical in geophysical models. It's called the traditional approximation, and in fact there have been quite a lot of works on by Karine Lucas, Antoine Rousseau, and collaborators on this subject to justify that this was a legitimate approximation. So the idea is that essentially you always end up with a movement that is more or less horizontal, so you can neglect what is happening in the local vertical. Okay, and so you want to look at the behavior of this system as eta goes to 0. So from now on, everything that I will be doing will be formal. So. So let's assume that you have a sequence u eta, rho eta that is compact. Okay, so assume that u eta behaves like some u naught plus eta u1 plus and so on, and same thing for rho eta. Okay, so I'm assuming that I have a compact sequence. Oui.
So you added la précédente.
I added what?
Viscous term the equation for you.
Yes, this was my tensor here that I never wanted to write. So here, typically, I'm taking the simplest possible diffusion. I'm assuming that it's isotropic. Okay, so it's not consistent with what I said earlier, but.
But you should put it on the OB model also.
Yes. Where is it? Yes. Thank you. Or maybe. So I'm assuming that I have a compact sequence. If I have a compact sequence, as you can see, necessarily in the limit, I will have a balance between the rotation, the pressure, and here my stratification term, or my gravitation term. So we have p eta, which is like 1 over eta, let's say p naught, even if it's not very consistent, plus p1 plus eta p2. Okay. Okay, so when I balance everything in the limit, what I have is E3 U naught plus gradient of P naught equals minus F minus 1 rho naught. Right? And in the last equation, it's very simple. I just have that the last component of U naught should vanish. Okay? Now, if I look separately, here there is an E3. If I look separately at the horizontal and the vertical component of this equation, what I find is that the horizontal part of U is the orthogonal gradient of the pressure, okay? And the derivative of the pressure is minus F minus 1 times rho naught, okay? So, as you can see, everything is determined by the pressure, and it's a two-dimensional model. And as many of you know, probably, when you're looking at 2D NavierStokes or Euler, it's convenient to introduce the vorticity associated with the equation. In that case, the vorticity itself is not completely sufficient. So what you introduce is a potential vorticity to take into account the dependency with respect to rho as well. Okay, so what you introduce is the following quantity. You introduce the potential vorticity, which is omega naught, and which is defined by d1 u02 minus d2 u01 minus f dz rho naught. Okay? And what you see is that this quantity is exactly the Laplacian of the pressure plus f square dz square of the pressure. So I can call this Laplacian f, by definition of Laplacian f of the pressure. Okay? And so then the question is, what will be the equation for omega naught? Okay? And you go back to the system here, and you write the next order in the approximation. Okay? So you have, well, you have two ways of doing this. Either you project onto the kernel of the anti-symmetric operator, but I will do this in a, let's say, a more pedestrian way. So what you have is the following. You have dt u0h, because u03 is 0, plus u0h gradient u0h, plus e3 u1, plus gradient of p1, minus Laplacian u0 equals minus f minus 1, well, 0 here because I'm looking at the horizontal component. Okay. Then I will also have dz, because I'm looking at the horizontal component. So here is u1h. And here is the gradient, and I'm looking, and you just have hydrostatic balance for the second equation. And now, when you look at the equation for rho naught, minus f minus 1 u3 or u13. Minus kappa Laplacian rho naught equals 0. Okay, and you also have divergence of u1 equals 0. And if you look at the structure that I have here and at the definition of my omega naught here, it's quite natural to take the gradient perp of the first equation and f dz of the second equation, and to sum up the two. Okay, so I'm taking gradient h perp of this one, and I'm taking minus f dz of this one, and I'm summing up. Okay, and if I do that, I end up with an equation for omega naught, which is dt omega naught plus u0h gradient h of omega naught minus some dissipation operator for omega naught equals 0. And the dissipation operator is Laplacian, coming from the two Laplacians that are right here. You have a Laplacian f minus 1, okay, just because p naught is Laplacian f minus 1 of omega naught, times Laplacian h plus kappa f square, yes, dz square, Laplacian f minus 1. Okay, so I'm going a bit quickly on this, but okay. When you take the gradient h-perp of the u0h that is here, what you get is the Laplacian of the pressure. Here, the horizontal Laplacian of the pressure. Here you have the vertical Laplacian of the pressure, but with a kappa in front of it. Okay, and then the pressure is Laplacian f minus 1 of omega naught. Okay, so I didn't specify any type of boundary condition whatsoever. So taking the Laplacian f minus 1 is a bit shaky. But let's say that you're working in the torus or in the whole space. Okay, so the Laplacian minus 1, you can just invert it in Fourier. And here, u0h, so is the gradient h-perp of Laplacian f minus 1 of omega naught. Okay? So it's really, it looks a lot like the vorticity formulation for Euler, okay? Except that you have an actual dependence with respect to z. Okay, and this is the quasi-geostrophic model. Okay, so obviously this is completely formal. There is one thing maybe that I should mention before ending my talk, is that in the case where f equals 1, this is a bit of a special case in the whole space case, because in that case you have no dispersion, I think, okay? Whereas if f is different from 1, you have dispersion in any case. So that's why I kept the parameter f all along and didn't choose f equals 1, because the case f equals 1 plays a specific role. So that's the reason. It's not that I'm crazy and I love having parameters everywhere. And I guess I will stop here for today. And so tomorrow I will focus mostly on this system to illustrate the filtering methods.
Thank you.